Hello, everybody. Um, Hope you all can hear me. Um,
Yes.
so Great. So thanks to Patrick and to Claudia for inviting us to speak at this event. So the presentation that I'm going to give today, and my co-author Terry Peters is going to give, is based on our 2018 book, Computing the Environment. This photograph is called Earthrise and was taken by astronaut Bill Anders in 1968 during the Apollo 8 mission, 7 months before the first lunar landing. This was one of the first photographs looking back at the Earth. Here we see the Earth as a finite closed system, with its nearest neighbor, the Moon, a desolate surface in the foreground. The Earth is revealed to be vulnerable in the infinite vastness of inhospitable space. As Carl Sagan wrote, the Earth is the only world known so far to harbor life. For the moment, the Earth is where we make our last stand. So we only have one Earth, so let's protect the environment. But this meeting today is about buildings. So what does architecture have to do with the environment and with climate change? Well, all buildings, even the most sustainable, use energy resources and produce emissions. So this is clearly one way that architect impacts the environment. However, I would like to take this discussion in a slightly different direction. The definition of what it means to be an architect is linked to design tools. As Jonathan Hill has pointed out, it was the invention of drawing that enabled the creation of the architect. Being an architect is defined by our ability to conceive of, to draw, and to communicate the plans for a building at or removed from construction. However, architects no longer draw on the drafting board, but now with the computer. But the computer is not the same as the drafting board, as Patrick has pointed out earlier today. And so with changes to our drawing technology come changes to our profession. New tools mean new ways of thinking. As computer scientist Alan Kay states, computational tools are no longer only rhetorical, but they are processes. They simulate and decide. And it is not just CAD anymore. 3D digital modeling, parametric design, generative design, BIM, big data, computer performance simulation, AI, etc. These are all now part of the architect's new drafting board. Through computation, architects are now able to realize the potential that Ivan Sutherland hinted at when he invented the first CAD system, Sketchpad, in 1963. Like the mech suit pictured here, digital design extends our abilities. So, architecture is related to drawing and also very much related to design. Architects design for the future. Necessary optimists, and to borrow from Herbert Simon, architects design to make existing situations into preferred ones. Architects, professionally and ethically, are driven to make a better world, not just for their clients, but for the population at large and for the environment as well. So, given that there is a climate crisis and buildings are part of this problem, they're impacting this crisis, and that design is now done using computation, how can our design technology help us? How can computation impact design to improve environmental performance? This was one of the driving questions for our book, Computing the Environment. The research done for this book comes from both Terry and my firsthand knowledge of architectural design and environmental simulation practices, but also for this book, we carried out interviews with architects and engineers from leading practices worldwide. One of the things that we found was that in every practice we interviewed, architects and engineers were using a whole constellation of different design technologies. Today, building designers must be able to navigate a constantly changing landscape of digital tools. For example, Building Energy Software Tools Index lists 147 software packages just for environmental design. And it's not just using tools, but developing their own tools. The designer has become the tool maker. So, Foster & Partners is one of the world's most well-known architectural practices. Founded in 1967, the practice has made significant impact on both design culture and our built environment. The office maintains a focus on sustainable design, drawing on both vernacular traditions and the latest building technologies. In the late 1990s, the office founded the Specialist Modeling Group, or SMG, to address the growing need for digital design expertise in geometry, building performance, and fabrication integration. I worked at Foster & Partners for many years as an associate partner with the SMG, designing and building projects such as this one here, the Kogod Courtyard at the Smithsonian. However, today I will talk about a Foster & Partners project that I did not work on, the Oceanwide project, a project that was done more recently and contains cutting-edge approaches to design, computation, and environmental simulation. While Foster & Partners uses MicroStation as the primary CAD software, the SMG and design teams use whatever digital design tools are necessary. For this project, a variety of software packages were used. The main structure and geometry were done using CATIA, the interiors used Revit, the facade was done using Dynamo, and Rhino was the go-to 3D CAD sketching environment. The SMG works between architectural geometry and engineering calculations. They develop custom digital tools that integrate engineering calculations within parametric geometry models so that they can more rapidly produce more relevant analysis, going from days or hours to even minutes. Xavier de Castellier, the former head of the SMG, says that the software that they customize sits between hardcore engineering tools and fluffy architect tools. Author Kjell Andersen writes that while design simulation is often seen as a specialist tool for predicting energy performance, the greatest value for architects is the freedom to play with design ideas and receive timely feedback. The SMG has written a custom tool for MicroStation that implements Radiance and have created their own wrapper for widely available environmental tools Ladybug and Honeybee, which they call LadyBee. A key part of the design for this project is at the ground floor where the building has been, quote, lifted up to create a new urban room that is open, accessible, and transparent. The project promotes a sustainable model of high-density mixed-use development. The team used performance simulation to understand the user experience in various ways: light levels, both artificial and natural, glare, the thermal environment, and acoustics. Over the last 10 years, the SMG has developed expertise in computational fluid dynamics, CFD, which is used to predict wind and airflow. A series of CFD simulations were carried out at various places around the tower and studied the influence of various building shapes on wind distribution. Both CFD and wind tunnel testing were done, but CFD offers considerable advantages as it can be completed much faster and in-house. The SMG ran simulations for 16 wind directions, and this data was combined with weather data. They found that the tower was intercepting wind at high level and pushing these winds down to lower levels. In response, the SMG designed a wind canopy so the wind doesn't reach the inhabited level. The SMG also found that the software architects use to compute the radiant environment is generally fairly inaccurate, and so they aim to develop new tools that predict performance with a level of confidence that is reasonable and yet still runs fairly fast. For the urban room, the design aspiration was to make sure the space was comfortable. Using the Universal Thermal Climate Index metric, the team simulated the public space along with similar spaces in the surrounding area for percentages of the year that are comfortable. Xavier de Castellier explains that we find ourselves in a middle ground, creating tools related to design, but that are still really accurate. Acoustic analysis was largely done with a plugin to Rhino called Pachyderm, an open source software that computes performance using ray tracing algorithms. Philip Robinson, the team's former acoustic expert, has found that importing geometry from CAD to commercially available simulation software to be an onerous process. But by using Pachyderm and Rhino, he is able to both design and simulate using the same software, and therefore does not have to bother with translation. As computational tools for environmental design mature, the potentials what teams like the SMG can do with them becomes much greater. SMG partner Irene Gallou speculates that simulation will give young architects a tool to understand the environment and to develop intuitions about the impact of architectural design on environmental performance. Thank you very much. I'm now going to hand it over to Terry Peters.
Okay, can everyone hear me okay? Yes.
Yes. Yes, great. Thank you very much. I am going to continue on and pull out some main points from the Computing the Environment book that Brady and I co-authored. So over the last 10 years, there has been an explosion in digital tools that designers can use. In the book, we examined a history of building performance tools from 1960 to present and created this diagram clearly inspired by Charles Jenks's 1973 graphic of architects and movements. And we looked at the recent history of building performance and simulation tools when they were introduced and really saw this huge explosion in the last 10 years and even increasingly in the last 5 years. So one of the main points that I'm going to draw out of the Computing the Environment book is this idea that of visualizing and visualization leading to understanding. So visualizing data allows us to understand it, to share it. That's how we can communicate and create trust between disciplines. To illustrate that, in the book, we interviewed GXN, which is the innovation group within Danish office 3XN. And talk to them about how they use digital tools, how they use simulation. And this example kind of illustrates that they regularly use environmental simulation on all of their design projects at early stage. And for this example of a new bank headquarters, they worked to take quite an abstract design idea, openness, connecting to the street, connecting to the public. The client's wishes, they wanted to translate this into creating a collaborative, comfortable environment for people working in this building. So how to translate these big ideas into architecture? A key was to use daylight to drive the building's form. In this image here, they used the Velux daylight visualizer tool to calculate the daylight factor for interior spaces, while considering the relationships between building geometry, orientation, views. And you can kind of see in the small photo there, the floor plate shifts in orientation as it moves up. So they used environmental simulation to get them to actually get visual feedback about design decisions. Rather than spreadsheets of data, they had visual graphics that allowed them to better make design decisions to bring them closer to design intent. So in this case, the goal wasn't about minimizing energy use and energy consumption, but actually their goal was for people to use the space, to enjoy the space, to be comfortable. And the client for Swedbank said, some people have been at the company for 25 years and only met each other for the first time the week they moved into the new headquarters. They had never crossed paths before, even though they worked in the same office. So it's this idea that they can use the feedback they get from their simulations to make design decisions to get closer to their design intent, in this case, for collaboration, for openness, for people enjoying the building. The second point I wanted to draw out of the Computing the Environment book is that data can also change behavior. So we can use data to change and understand people's behavior in buildings using real-time feedback. Another project from 3XN is their Green Solution House. It's a hotel and conference center in Denmark. I'm using it to illustrate the idea that some of the new metrics for sustainable buildings and for energy consumption are not easy to visualize. With this kind of data, if you can't communicate the findings, it's sort of limited use. So in this project, inside the hotel rooms, there is actually a dashboard, and it allows you to see in real time how you're using energy, like how you're using electricity, water. What else can you see on this? Sort of energy, light, air, and water use. And it actually allows you to see what proportion of the energy you're using is from renewable sources. And people staying in the hotel room, say they're going out for the day, they can kind of see, oh, I'm still using electricity. That's weird. And they can go back around the room and maybe unplug something or maybe turn the bathroom light off. So it really drives home this idea that people are using the energy in buildings rather than buildings using energy. So this is called the Smart Room Collective Monitoring Project, and it was a collaboration with GXN and Autodesk Research. And it really addressed this idea that visualizing data is a really important part of collecting the data and really putting action to it. So kind of looks at communication of data. And these are the nice rooms at the hotel here. So the third point I'm going to talk about is designing for microclimate. So collecting and using on-site data, microclimate data, to inform simulations. Another office that we interviewed is Kieran Timberlake, American office Kieran Timberlake. And they use real-time environmental feedback as a design tool in their projects. We interviewed them about how they use digital design tools, which tools they use, how they use them in projects. And we were kind of surprised to find that in recent projects, they are really interested in collecting microclimate data on their sites. So they're actually installing weather stations on site on different projects. And recently they installed 10 custom weather stations on project sites. So rather than relying on more general climate data, like TMY files for a specific location, they're actually collecting their own data to input into their simulations. They also do some renovations, and they're looking at collecting really accurate on-site, site-specific data about the renovations that they're starting with in order to be able to develop responses that really connect to the existing conditions. And the next point I'll talk about is sharing data. Considering interoperability, workflows with different tools, sharing data. This is obviously a huge issue in practice. In the book, we looked at many digital design tools that practices use in the 12 profiles of offices. We looked at what kinds of sustainable design parameters the different tools account for. And we mapped these into the sort of lead categories and really examined what kind of digital tools people are using. And something we touch on in the book is how we need to use collective intelligence and shared insights to be able to interpret and really use the data that we collect about buildings. Kind of looking at the building performance and the relationship between design intent and buildings in use more carefully so that we can compare them and make better predictions. In the book, we featured Toronto office Diamond Schmidt Architects and their database for collecting, comparing, and analyzing energy use in buildings that they design. So this is called Ecometrics, and they're able to collect data and compare it across a number of projects that they design in the office. And then they have a really informed starting point for the next project that comes into the office. They already have an idea of what techniques have worked, what are reasonable assumptions to make or aspirations to have about design performance. And this is really rarely done in an office. And if it is done, people weren't sharing it with us. We talked to people about how do you collect and map the building data that you have for all of your projects and compare it to one another. You're collecting all this data. How are you using it? And we think that there are still a lot of barriers about sharing data within offices, even beyond externally. So that I think that's an area that I could see practice sort of developing in the future. The last point I'm going to talk about is, I guess, the idea that it's hard to care about the environment and it's easier to care about ourselves. So I think reframing sustainable design as design for well-being and design for people is a really important way of getting more buy-in and people making more effort in sustainable design. And I'm thinking, like, what kind of building data would you collect if you were concerned with people's health and well-being, if that was driving the design? And what kind of feedback would you need or want? So many of you are familiar with this idea that in a building, for typical business operating costs, it's not the energy costs, it's not the real estate costs, it's the people that are the valuable asset here. It's training staff, recruiting staff, keeping staff. It's the people, and it's also the people that use the energy in buildings. So really understanding more in detail how people use buildings and the sort of the impact that people have on buildings. So sustainable buildings need sustainable users, yet occupancy and occupant data is really one of the areas of environmental design and environmental simulation that we have the least information for. So many of you might be familiar with the COGA effect studies that in green buildings, people seem to perform better in cognitive tests. So green buildings and enhanced ventilation are really important for sustainable buildings, but also for people's performance in buildings. There's a lot of different aspects that we could explore using simulation relating to what makes spaces both healthier and more environmentally better performing. For example, biophilia, connection to nature, and different ways of looking at lighting. So, for example, in biophilic design, it's becoming more relevant as it becomes a measured aspect of, for example, the WELL building standard and living building challenge. So one of the principles of biophilic design is thermal and airflow variability in spaces. So the subtle changes in air temperature, relative humidity, airflow across the skin. This idea that we can use design tools and the designers should be designing for variability is something that we can do with building simulation tools. And we have new tools like the Alpha tool for circadian lighting, which is a way of measuring and evaluating lighting in buildings that connects to more human-centric approaches. So to sum up, I've talked about some key issues in computing the environment, this idea that visualization equals understanding, data can change behavior, designing for microclimate, sharing data, and we are the environment. Thanks very much.